Okay, so in this video I'm going to talk about the heat equation with different boundary conditions. So we are going to look to different boundary conditions and initial conditions as well, and we are going to sort them out, and we are going to tell how we can utilize the boundary conditions and the initial conditions as well in order to represent our heat equation. Okay, so let's go and jump directly to the first part. Remember that our main equation is still the same. As we said, this is partial u partial t is related to partial squared u partial x squared with a constant k, which is, we call it, it is depending on the medium. So this equation can be solved. We are going to solve it because this is a partial differential equation. We want to solve it, right? So it can be solved subject to a variety of boundary and initial conditions. So we need to think about what are the boundary conditions that we have, what are the initial conditions that we have in order to solve this equation. Okay, so let's start with the first type of boundary condition. Okay, let's assume that we have a bar, okay, and we want to model the temperature distribution along this bar. It's like a thin homogeneous bar or homogeneous bar of length L. So it has a length L whose left end is kept at temperature T1. So left end means that at x equal to 0, and it is kept at temperature T1. However, the right side or the right end, which is x equal to L, it is kept to another constant temperature T2. Okay, so if we want this, we want to, like, these are the boundary conditions, and we have an initial condition that at the profile of the temperature along this bar is going to be like function. So this is going to be like a function of x, f of x. Okay, so at t equal to 0, which is the initial condition for us, we are going to say that the bar is having the function f of x. Okay, so let's read what I have said now, or what I have explained now based on the boundary condition and initial conditions. Let's read it in a mathematical form. So we are going to say that our function, which is the differential or the partial differential equation, is going to work for us from the left end to the right end. This means from 0 to L, where x is going to range between 0 to L. And this is, we are going to describe it for any time starting from 0, right? Starting from whatever is larger than 0. Okay. And then we said that our left end means x equal to 0, so it is going to be kept at temperature T1. So u of 0 and t equal to T1, right? And then the right end is going to be at x equal to L, so u of L and t equal to T2. This is going to be for t larger than or equal to 0, right? Because we are considering here the initial conditions is going to be like included in our case, so we have the equal here. Okay. And then u of x and 0, this means what? Exactly the initial condition at t equal to 0. We said that there is a profile, this is the bar, and there is a profile here at t equal to 0. This profile is going to be f of x along the bar. So u of x at 0, x at t equal to 0 equal to f of x for x between 0 and L with equal here. Do you remember the three axes that I have mentioned before? This is here x, this is t, and this is uppercase T. So at t equal to 0 here, we're going to start with a function. This is the function that we are having here, which is f of x. Okay, this is f of x. This is what we are talking about here. Okay? Okay, so this is one type of boundary conditions and initial conditions that we can use to solve our differential equation. Let's go to another type of boundary and initial condition. Okay, we call it the initial boundary value problem. Let's assume that we want to model a bar, and we want to model the distribution in a bar of a length L, this is L here, having no heat, look here, having no heat loss across its ends. No means zero. Heat loss means that partial u partial x, there is no heat loss across its ends. We are talking about the ends, means that x equal to 0 and x equal to L, right? So this means that at x equal to 0 and x equal to L, we are going to have partial u partial x equal to 0, and here partial u partial x is going to be 0 as well, right? So that's the meaning of what we are talking about here. We call this case insulation conditions. And initial temperature function is going to be F. Initial here means what? T equal to 0. Okay, so we can interpret this in a mathematical way or form using these equations here. We are going to have our differential equation for the rod or this bar, which is having a length of L. So we're talking from 0 to L, and it is going to work for us starting from T larger than 0. Okay, and then we are going to have the heat loss, okay, which is like the heat flow. So we are going to talk about partial u partial x at the beginning at x equal to 0, and partial u partial x at the end, which is the right end, at x equal to L, with any time t, or at any time t, both of them, they are going to be 0, right? Because why? We said that no heat loss across it. So no means that 0. For t larger than or equal to 0. This is including t equal to 0, of course. Okay, so now for u, x, and 0, which is the initial temperature, we said that the initial temperature distribution at t equal to 0 is going to be with a function f of x. We are going to have a function something like this. Okay, so this is going to be our function, and this function is going to be starting from 0 to L. Starting from 0, this is 0 here, to L. This is our function. Okay, so this is what we call it, the initial boundary value problem, and we have modeled this boundary condition and initial conditions using these mathematical equations. Okay, now let's go to another type, another kind of boundary conditions. We're talking about boundary conditions here, also can be specified. Let's assume that if the left end means what? At x equal to 0 is kept at constant temperature T. So it is going to be at constant temperature T. So u of 0, which is x equal to 0, as we said, left end, at any time t, the temperature of this end is going to be constant T. And the right end, which means that at x equal to L, is insulated. We said what is the meaning of insulated, right? We mentioned that no flow of the heat with respect to x. So this means what? Exactly that partial u partial x heat flow across or along the bar length, okay, at this point, which is at x equal to L, which is the right end, at any time t, means that it will not be variant with time. It is going to be constant, always constant, okay, with the value of 0. Okay, so this is how we can put it in this form. So we are going to say that u of 0 and t, to this part, left end is going to be at temperature T. However, in the right end, it is going to be exactly partial U partial X of L and T equal to 0. This is for any value or for any time larger than 0, of course, right? Okay, so now this is the case of one of the boundary conditions. Another boundary condition, we call it free radiation or convection. We call this like free radiation or convection. It occurs when the bar loses energy by radiation. Okay, radiation means that the bar like this, and there is like radiation from the bar to the surrounding environment. From its ends, this is along the bar, but here I'm not talking about the bar, all the bar, I'm talking about the ends. So the end, maybe the end itself is radiating, okay, from its ends into the surrounding medium, which is assumed to be maintained at a constant temperature T. The medium outside is going to be T always. Now, the boundary conditions have the form, or boundary condition is what is going to have this form. In this specific case, not in this here, we're talking about here and here. As we said, radiation. So this means that like changing, okay, changing radiation from its ends is going to be partial U partial X at X equal to 0. This means that the left end at any time T, it is going to equal to something like this. A constant A, which is a positive constant, times U of 0 and T, which is the value of temperature at the left end at any time, minus T, which is the surrounding medium temperature. And also, it is going to be, on the right end, is going to be partial U partial X at X equal to L, which is the right end, at any time T equals to minus a U of L, capital L, and T minus T. Okay, this is always minus. Why? Because of this. We say that, we're going to say here, explain it. Notice that if the bar is kept hotter than the surrounding medium, then the heat flow, this is what we call it, partial U partial X. The heat flow as measured by partial U partial X must be positive at one end and negative at the other. So we are assuming that here this is going to be positive, as if radiating the heat, here as if it is absorbing the heat. Okay, this is how it works for this free radiation. It is what we call it the case of free radiation or convection. Okay, now another boundary condition, which is going to be the case where that we want the left end, this left end between X equal to 0 is kept at a constant temperature T1. So this is constant temperature, so U of 0 and T equal to T1, while the right end radiates. The right end radiates heat energy into a medium of constant temperature T2. So it is radiating here. This means that at X equal to L, this end is radiating energy. So this means that partial U partial X should equal something. This thing is here, which is minus a U of L and T minus T2. Okay, where T2 is what? The medium constant temperature. Medium constant temperature. Okay, great. Let's go now to the next part. Maybe this would be requiring another video. This is the end of this video, where that we have explained different boundary conditions for the heat equation that is going to help us to solve it. Okay, thank you, and see you in the next video.